All right, hi everybody, and welcome to today's session of the Spectral Geometry in the Clouds seminar. Just as a usual reminder, the talk is recorded. Today we have as our speaker Christiane Tretter from the University of Bern, who will talk to us about spectral problems on star graphs. As usual, if you have a question during the seminar, you may either unmute yourself and ask your question, or you may ask your question in chat, in which case I will relay the question to the speaker. And well, the floor is yours now, Christiane.
Yeah, thank you very much, Jean, for the invitation to give a talk in this so nicely entitled seminar series. So I felt inspired to choose a new title page just before, like an hour ago. So I was looking for some beautiful clouds here near Bern, but you won't see so beautiful clouds today. It's actually a little bit more rainy. So my talk today will be based on joint work with various people. So there will be papers with Slava Pivovarchik and Natalia Rozhenko on the one hand, in the more or less first 2/3 of the talk. And then in the last part of the talk, I'll talk about some more recent work with Malcolm Brown and Heinz Langer. So the common theme in both these parts are star graphs. And in the first 2/3, it will be some more concrete star graphs, namely star graphs made out of Stieltjes strings. And so I would like to just introduce you a little bit to this rather classical topic, first of a single Stieltjes string. So the key contribution here is due to Gantmacher and Krein in 41 and 50, their book, and especially the appendix therein. So a Stieltjes string is an elastic string of zero density bearing a number n, finite or infinite, of point masses. In the first part of the talk, we will assume that this number is finite. If later on it is allowed to be infinite, then accumulation only at one endpoint will be allowed. So in the finite case, we have n masses sitting on such a string here. And on the boundary points, there are no masses sitting, so they are only in the interior, and L0 up to Ln are the lengths of the intervals between them. And there are two problems that we will consider here. So on one endpoint on the left here, we will always have a Dirichlet condition. And then on the right endpoint, we will either have Dirichlet or Neumann condition. Now, I can even show you a real Stieltjes string thanks to this paper of Cox, Embray, and Håkansson, which appeared in 2012. So they even made some experiments for inverse problems of such Stieltjes strings. So here you see 6 masses and all these devices measuring stuff. And really also the article is nicely written, also giving the history of the Stieltjes strings. So if you want to learn a little bit, then I would recommend this. Now, the equations of motion that we will now derive on the next slide, the notation is that, so we have these these n masses, M1 to Mn, and by Vk of t, we denote the transverse displacements of these masses at time t. Now for k equal to 0 and n plus 1, we have the left and the right endpoint of the string and use the corresponding notation. Now the Lagrange equations are then as follows. So you have these two difference quotients and then plus mk vk double prime of t equal to 0 for k from 1 to n. Now the boundary conditions. So we have these two different problems. For the Dirichlet problem, so left and right endpoint, we simply have the displacements have to be 0. And for the Dirichlet-Neumann problem, where on the right-hand side we have a Neumann condition, this slope here has to be equal to 0. Now, as usual, separation of variables in this form, Vk of t equal to uk times e to the I lambda t leads to the following system. So from the Lagrange equations, we get these difference equations here. Here is now the spectral parameter is the lambda squared, which comes from the second time derivative. And then here we have the Dirichlet conditions and the Dirichlet-Neumann conditions for the amplitudes uk. Now, in the appendix of the Gochberg-Krein second edition, so which appeared in 1950, the title of this appendix has two parts, and the first part especially reads nicely in German. It says, eine bemerkenswerte Aufgabe für eine Perlenschnur. So that's also a little bit old-fashioned German. And translated literally, it means a remarkable problem for a string of pearls. And so this is the equations that we have from the previous slide. And now what Gochberg and Krein did in this appendix, so they derived a two-term recurrence relation for these amplitudes. So namely, if we set z equal to lambda squared and solve for uk plus 1 in these equations here, we get the following recurrences. So uk plus 1, so this is equal to some polynomial with an even index r2k of z applied to the u1. And this quotient here, uk plus 1 minus uk over the length lk between the masses, is an odd integer polynomial r of z applied to u1. And these polynomials, r2k and r2k minus 1, they are polynomials of degree k, and they satisfy these recurrence relations that you can see here. So basically, each of them is expressed by the two predecessors. The difference between the two equations is that for the odd ones, you have a coefficient minus mkz sitting in front of the next lowest. And for the even ones, you have the length lk without a z here in the recurrence relation. So if we now want to solve the Dirichlet and Dirichlet-Neumann problem, so first of all, the Dirichlet on the left-hand side means that u0 has to be equal to 0. So in this case, we can choose r minus 1 of z to be equal to 1 over the length, the first length next to the left endpoint 1L0, and then r0 of z equal to 1 to start the recurrence at k equal to 0. And then at the other endpoint, we have the following two conditions for the amplitudes. For the Dirichlet, the amplitude has to be 0. So if we look up here, we see that means simply that R2n of z, or of lambda squared, has to be 0. And this is the equation for the Dirichlet eigenvalues lambda. Now for the Dirichlet-Neumann eigenvalues, we have this condition at the right. And correspondingly, if we look up here, so we have to have, this is 0 if the odd polynomials are 0. So the Neumann eigenvalues, or the eigenvalues of the Dirichlet-Neumann, to be precise, a problem that we consider here are the zeros of these odd index polynomials. So now on the next slide, we will consider the quotient of these two. So we see that the Dirichlet and Neumann eigenvalues will be the zeros and poles of the quotient formed out of these two polynomials here. And this brings us to the second part of the title of this appendix in the Kochberg-Krein second edition of 1950 book, which is called Und über Stieltjesche Kettenbrüche in German, so and on continued fraction expansions. So this is the quotient I was mentioning from the slide before. So let's call that phi of z. Now these quotients, let me just go back for a moment to the formulas, to the recurrence relations. So we will now look at quotients of these two, and then, not of these two, so, sorry, we divide by this term here, and then we see that the quotient satisfies certain relations, and we will successively insert these relations. Here is the first one, and then we do it again for this quotient. So once we get the ln, because we had these two different first coefficients, and in the next place we get minus mnz, and then ln minus 1, minus mn minus 1z, etc., until we end up with 1 over L0 minus m1z plus 1 over L0 here. So this phi, of which the Dirichlet and Neumann eigenvalues are the zeros and the poles, has such a representation here, where the ln and the mn are the masses, the length of the intervals, and the masses on the Stieltjes string. Now, maybe we can note at this stage, if we plug in 0 here, then all the L's pile up to the numerator, and we get the sum of all the L's, which is the total length of the string. Now, these continued fractions were studied by Stieltjes in a work dating back to 1894. And you see the title page here. And even if you cannot recognize precisely what's written there, I think what you can recognize is that structure here is the same as here. The difference being that these continued fractions here are not ending. So these are infinite continued fractions in this work. Now, it was only in the Kochberg-Krein appendix that these considerations of Stieltjes on continued fraction expansions were given a mechanical interpretation in terms of these strings, which maybe because of that were then called Stieltjes strings, right? So let's go a little bit more into detail here. So first of all, this function phi, as we shall see, has a very particular property. Not surprisingly, it's called a Stieltjes function. And why? What is a Stieltjes function? A Stieltjes function is a function that is a Nevanliner function. So it's a function analytic in the complex plane without the non-negative axis, mapping the upper half plane onto itself. To be a Stieltjes function, in addition, it is required that f of z is greater than 0 when z is on the negative axis. And a subclass of Stieltjes functions, S0 functions, are those for which 0 is not a pole. Now, this phi that we see up there is an S0 function. So how can we see that? There is the following lemma, which I restrict myself to the case of rational functions, because our phi, because we have only finitely many masses, is a rational function. So f is a rational S0 function. If this is the first direction, if f is a rational S0 function, then it has a continued fraction expansion as follows. So there exists a number p, and unique a0, which is the limit at plus minus infinity of this function f. So this is greater than or equal to 0, and coefficients ak and bk all greater than 0, such that this f has a continued fraction expansion like that. It's finite because we assume that f is rational. And moreover, the zeros and the poles of this f strictly interlace in the way you can see it here. So it starts with alpha 1, then this is less than beta 1, and so on, up to alpha p, and beta p appears in the case that a0 is greater than 0. Vice versa, if f is rational with strictly interlacing zeros and poles, as in this relation star here, and the limits at plus minus infinity are non-negative, then f is an S0 function. And this is how you can then see that this phi is an S0 function. Now, in this particular case of the phi, just to recall and to make the connection, the coefficients in this continued fraction expansion, the A0, it's numbered the other way around. So the A0 is the length number Ln. So the length to the very right of the string. And the AK are the lengths Ln minus K. And the coefficients Bk are the masses number Mn minus K plus 1. And the f of 0, this is the sum of all the A's. And in our case, this is then the sum of all the L's. So this is equal to L, and this is greater than 0. So therefore, we have all the properties that we need. Now, we want to solve the inverse problem for this Stieltjes string. So again, this was done by Gochberg and Krein in this appendix. So the inverse problem is as follows. Given is a number n in n and two sets of strictly interlacing numbers lambda 1 to lambda n and zeta 1 to zeta n, together with a length L greater than 0. And the task is to find masses mk and lengths lk between them, so that the zeta k and the lambda k are the Dirichlet and Neumann eigenvalues of the corresponding Stieltjes string of length L. Now this problem can be solved. This is the solution. So you introduce a function capital psi. You take L, this is the length, times the following quotient. So you build these products with the sequences zeta k squared and lambda k squared and form the quotient. Then for sure psi of 0 is equal to L. That is one condition we want to have. Because of this interlacing property and all the assumptions, this psi turns out to be an S0 function by the previous lemma. And therefore, it admits a unique continued fraction expansion. This is the continued fraction expansion. And now we can read off the solution of the inverse problem from that continued fraction expansion. Right? In the same way as we did it before. So the Ln is the A0, the Lk is the An minus K, and the B are related to the masses in the same way as we had it on the previous slide. So this is the constructive solution of the inverse problem for a single Stieltjes string. Now we will move on to star graphs of Stieltjes strings. And here is another nice picture, which I think Mark Embray showed this to me quite some time ago. So there are really instruments built from such star graphs. This is with 3 strings. Okay, it's not Stieltjes strings, but it's a star-shaped vibrating system. And you can even listen to these things and maybe just to have a little break. I'm not sure, and let's see if you can hear what I hear. If you can't, I will do something else. let me do it differently, because I have another computer next to me, and I'll try to play this to you. Where are we? I will now go down to the microphone so that the microphone comes to the speaker, and let me try if you can hear it. So I hope you could hear it, because it came through the same microphone as my voice. A very weird sound, I think.
We heard it very well.
A very, very strange sound. There are more such examples that you can listen to. Well, the only thing that this system has in common with ours is, well, it's somehow a planar star graph, and that will also be the case in our new situation. So a star graph of Stieltjes strings, here still with a finite number of masses. And we will have the following setup. At all the outer vertices, we will have Dirichlet conditions. And then in the middle, in the center of the star, there is a new element here compared to the previous setup, because we can have a mass there. Remember, before we didn't have masses at endpoints of Stieltjes strings. So this capital M is the mass at the center. It can be 0, but it can be present. And we will consider in this center 2 different types of conditions. The Dirichlet condition, well, in that case, you won't feel the mass anyway. And if the Neumann condition is there, you will feel it. So what is the notation? So the number of strings we consider is Q, greater than 2, greater than or equal to 2. Then the strings are labeled with a J, and all the corresponding numbers, Nj, the number of masses, and the length, Nj, the total length of the string number J, they all have this J label here. And on each string, we have the masses Mk, and then I have to put the J maybe in another place, and the Lks. So as you see it in the picture, the ordering of the masses is always from the exterior, counted from the exterior to the interior. And then there is this possible mass M greater than or equal to 0 at the central vertex. And we will consider 2 problems, a little bit similar as before. So always Dirichlet conditions at the pendant vertices plus continuity. And then the rather trivial problem where we also put, a Dirichlet condition at the central vertex. This is the problem D1. And the other problem, Neumann condition at the central vertex, will be called N1. The one will be basically a little bit superfluous in this talk, because I will not talk about the other problems, D2 and N2, in the paper. They corresponded to the case when this change of the condition that we have in the center of the star graph here was not in the center, but at an outer vertex. So we have also treated this problem, but I would like to concentrate just on this with the middle point as the root. Okay, so what are the 2 problems? So we have the equations for a single Stieltjes string here that we had before, now labeled with the J in addition. And then we have the 2 Dirichlet conditions as before. So here really just Q Stieltjes strings glued together and non-interacting, because we have the Dirichlet condition at the central vertex. The other problem is different. So the first equations are the same. The Dirichlet conditions at the outer vertices are the same. Now the continuity is a bit different, because they are now not 0, just equal. And the Neumann condition at the central vertex now takes the form that you can see here. So because we can have this mass capital M in the middle, we don't have 0 here in general, but we have m times the spectral parameter lambda squared. So as here, it also appears in one of the vertex conditions, in the matching condition. Okay, now the direct spectral problem. The first, before you can solve an inverse problem, of course, you have to first find out what are the direct properties so that you know what the assumptions are that you have to meet with sequences that you are given. So the Dirichlet and Neumann eigenvalues of the two problems we saw on the slide before turn out to be the zeros and poles of a function phi q, which is again the quotient of two functions, phi dq and phi nq. And this, if you really work it out, you see that this quotient is given as follows. So 1 over, then you have the sum over all strings, then 1 over the functions phi j. These are the same functions phi that we had for a single string before, but now labeled for each string, and then minus m times the mass times z, the central mass times z. And the second claim is that after cancellation of possible common factors between the two functions here, this function phi q becomes an S0 function, a Stieltjes function of class S0. Now, a few remarks here. So the numerator here, the phi dq, this is nothing but the product of the individual functions phi j corresponding to the Dirichlet, to the single string, right, that we had before in the first section. Now, the number of the Dirichlet eigenvalues you can work out to be n, namely, this is just adding up all the numbers of Dirichlet eigenvalues on the individual strings. Now, the number of the Neumann eigenvalues, let's call them again lambda k. This is different if this mass is there in the center or not. It's n if the mass is 0, and it's n plus 1 if it's greater than 0. And now in the next result, we will now prove some or formulate some properties that we proved for these Dirichlet and Neumann eigenvalues. So these sequences, well, either up to n or n plus 1, you can always set lambda n plus 1 equal to infinity if you want to formulate it in a uniform way for both problems here. So these sequences of the squares of the Dirichlet and Neumann eigenvalues, or the sequences themselves, satisfy the following properties. The first one is an interlacing property between them. And there are a few strict inequalities in here. Well, first of all, lambda 1 is greater than 0. And this is for the case, I have to say, that m is greater than 0, right? So we will now focus on that case, if m is greater than 0, because that would make a difference here. But then in particular, the first two, lambda 1 and zeta 1, satisfy a strict inequality between them, and the same here between zeta n and lambda n plus 1. Now, the second property is a Dirichlet eigenvalue, or let's rather put it like that, a Neumann eigenvalue lambda k is equal to the previous zeta k minus 1, if and only if it's also equal to the next larger Dirichlet eigenvalue for all k from 2 to n. Then the multiplicity of each lambda k cannot exceed q minus 1. Now, what's maybe an interesting consequence of that result is the following corollary. So if you look at two neighboring Neumann eigenvalues, then because of these properties here, one of them must be simple, right? Otherwise, you get a contradiction to the properties in theorem 2. So now we have the ingredients that we can move almost to the inverse problem, but let me maybe comment on one thing before. That's not directly related to the inverse problem. Let me maybe go back to make this comment. So here we don't consider any dependence of the eigenvalues on this central mass M. But if you once think back to this Dirichlet problem, so you could imagine the Dirichlet problem to be the one where this mass is infinite. Because if you put an infinitely heavy mass in the center, this is really, nothing can move. It's like a Dirichlet condition. So then you can consider the dependence of these eigenvalues lambda k on this mass M, right? And so the zeta k would be basically the value of lambda k at M equal to infinity. And in fact, the lambda k depend on M in a monotonic way, namely they decrease monotonically when M increases, right? So, for example, the lambda 2, when M grows, decreases to zeta 1, and then in the limit, it becomes zeta 1, right? And the lambda 1 for M tending to infinity decreases to 0, and so on. So this is what you see here. So the lambda 1 viewed as a function of the mass M tends to 0. The lambda k plus 1 tends to the zeta k. So somehow the Dirichlet problem is the limiting case M equal to infinity of this Neumann problem, if you want to view it in this way. By the way, you can prove this property, the monotonicity property, also using the Sumner-Van Lina properties of the functions involved. So now, what is the inverse problem we are considering here? So what is given? First of all, the number of strings is given, Q. Then the total number of masses on the star graph is given. Then the lengths of each of the strings is given, all greater than 0. And in addition to that, two sequences, zeta k squared and lambda k squared, satisfying the three assumptions, or I mean the properties they must have to qualify to be a set of Dirichlet and Neumann eigenvalues of such a star graph of Stieltjes strings. Question is, can we now find the number of masses on each string and the distributions of these masses then on each string, so that these are the Dirichlet and Neumann eigenvalues? And the answer is yes. One can construct the numbers nj of masses on each string, and then all the masses on the strings, including the central mass, and all the length between these masses, so that we get the total number n, the prescribed one, and the lengths add up to the total length of each string. And in such a way that the given sequences are the Dirichlet and Neumann eigenvalues of the corresponding star graph of Stieltjes strings. Now, the proof is a bit more involved than the one I showed you for the single string case, so I will not say much about it now. I mentioned already that we have analogous results when this root where we change the boundary condition between Dirichlet and Neumann is not the center of the star graph, but when the root is at a pendant vertex, at an outer vertex. Okay, so now we go to a different setup. This is now the second part about the second paper, the more recent paper with Malcolm and Heinz. And this is very different in nature because it's nothing concrete to start with. And even the star graph that I plotted here is more symbolic at this stage. Because what we will actually consider is Q plus 1 symmetric linear relations with equal defect numbers 1. They could, for example, be induced by some differential operators on edges. But for the moment, they are just abstract, and they will be joined by some self-adjoint matching condition. So by joining these, we will obtain some self-adjoint operator T, A, B. I will say a little bit more about this notation with the A, B in a minute. Now, a setup like this was considered, for example, already in a paper by Simonov and Voracek in 2014. But they considered different questions, or we consider completely different questions than they did. So what are we interested in? You see already that I distinguished one edge in color, which we, and also in the enumeration, which I call E0. And we will ask the following question. For a fixed edge, let's call it E0, is there a simpler system that in some sense, which will be made precise more later, coincides on E0 with the original one? And secondly, if all the edges are of one type, for example, as we had it before, all Stieltjes strings, can then this new part, which contributes to this simpler system, be chosen of the same type? So this is, of course, a much different nature of questions that we are considering here. And the answer is that, well, yes, in the first case, yes. In the second case, it depends a little bit, but in many cases also yes. And to arrive at these answers, I will now a little bit schematically describe to you the two-step reduction procedure by means of which we arrive at that simpler system. And then we may make more precise what means coincides and what is the answer to the next question. So here is this star graph again with a distinguished edge, and the V, by the way, is the central vertex. So the first reduction step is that we will basically condense this whole blue part into a boundary condition. So after the first step, we will arrive at a problem or an operator or symmetric linear relation just on this edge E0, or just one, but on this one side, if you want to view it symbolically of the edge, we will impose a boundary condition which will depend on a parameter Z. So the blue stuff is now all absorbed in this blue, well, non-standard boundary condition with this parameter or spectral parameter dependent condition. So this is the first step, right? So how is this going? How do we arrive at this coefficient here? So first of all, let's go a little bit through the notation. So we have these individual symmetric linear relations. We form a direct sum. So if each of them has defect number 1, then the sum, we have q plus 1, has defect number q plus 1. And now we want a self-adjoint object created from this. So we need to restrict the T star, the adjoint of this, by some condition which gives us something self-adjoint. And you will recognize this. It's very similar to the usual matching conditions that you know from considering concrete systems on star graphs. The difference here being that these objects gamma 1 and gamma 2, they are now abstract. They are coming from boundary triples for this T star. So for every symmetric linear relation, you have such boundary triples. And so we have them for each Tj star and for the big Tj star as well, because here we have defect 1. The first space in this boundary triple is 1-dimensional. Here we have defect q plus 1, so it's q plus 1-dimensional. So just imagine this TAB is now a self-adjoint restriction of this T star by such a condition here. And now we showed that these systems here are in some sense equivalent if we choose for this n0 of z the following function. So we need the individual Weil-Titchmarsh functions on these. They are defined for each such symmetric linear relation on an edge, or for the Tj, the phi j. Then we form out of all these phi j a diagonal matrix, which we call script M. And then we have these two A and B, these matrices, from the matching conditions defining our self-adjoint linear relation here. Now we do the following. We have a quotient 1 over a number, depending on z, so a function of z, which appears as follows. So we take a scalar product in CQ plus 1, namely of the following objects. We multiply A with not the full diagonal Weil-Titchmarsh function, but we replace the first phi 0 by 0. So this is MQ, where we only take phi 1 up to phi q. So then we multiply this. This is a function of z. We subtract b. Then we show this is invertible. We take the inverse, apply it again to A, and then to the vector E0, which has just a 1 in the first component, and then take the scalar product again with E0 or epsilon 0. So that's the definition of this function. And we also show that this N0 happens to be an Evan-Linder function. This will be important in the following. So maybe because this looks all a little bit very abstract, let's have a look what we get for this N0 in a more particular case. Let's, for example, look at what you would know as Robin type matching conditions for these linear relations, or if you think of a concrete realization, what you would know as Robin type matching conditions. So these are these matrices describing the Robin type conditions, and here we have a parameter 1 over tau. So this corresponds for tau equal to infinity. I haven't written down the matrices, but tau equal to infinity, this corresponds to Dirac conditions, and tau equal to 0 to standard matching conditions. In this case, if you work out the formula that you saw earlier, then the N0 takes this particular form, actually much nicer and simpler. But of course, here the AR and the BR, they have a lot of zeros, so they give very nice results. So it's 1 over tau plus the same sum that we saw already in the first part of the talk. So the sum over all 1 over phi j over all the blue edges, right? So here we sum only from 1 to q, only the blue edges. And the phi j are the Weil-Titchmarsh functions of these linear relations of the edges 1 to q. So this is a very nice form, and this is the N0 which goes into this condition here. Now the second step is now, at least as involved, because now we unfold this boundary condition at this formally central vertex V in quotation marks in our symbolic scheme. We unfold this to a new linear relation, or if you wish on an edge, just a new linear relation which we join to the distinguished one. So how do we do that? Well, here we don't do so much ourselves, but we use a number of very strong inverse results, because it is known that since N0 is a Evan-Linder function, we can apply various inverse results to obtain that we can join to this original E0 and T0, the symmetric linear relation on the distinguished edge, always a symmetric linear relation T1 tilde, And joining here at this V means with standard matching conditions. So even if we started with something with A and B here at this reduced system at the end, it will be standard matching conditions at V. Now, we can also join other things. For example, we can use the branch's inverse result to get a trace normed canonical system T1 tilde. And in this case, then the E1 tilde is nothing abstract. It's really an edge, for example, for simplicity of infinite length, if you like. Now, in the particular case that our N0 happens to be not just a Nevanlina function, but a Stieltjes function, then we can apply an inverse result of Krein to obtain the T1 tilde in the form of a Krein string, which is something more general than a Stieltjes string, on an edge E1 tilde. And in all the cases, these objects that we obtained here on this newly added part, E1 tilde, they are all joined to the distinguished T0 by means of standard matching conditions. So this I will denote by A0, B0 somehow. So altogether, somehow we reduced first this blue part here. First, we condensed it into one boundary condition, and then by means of all these different inverse results, we unfolded this spectral parameter dependent boundary condition into a new system, and we have some influence on what type this system has. So to give you an idea, it has been quite abstract with all these linear relations so far, but what could these linear relations really be induced by? So the possible types of realizations on edges of a star graph that would give rise to such a system that we can cover is, for example, a canonical system. Like that, including also Dirac systems. Then it could also be a Krein string. Here we see that this is more general because a Stieltjes string is a Krein string where the mass distribution M, which is not the M from the first part, here is now a step function making steps on where the discrete masses are sitting. Or it could be a Sturm-Liouville problem that gives rise to this symmetric linear relation, right? And now we can ask the question, what is the structure of the reduced system if we have some structure of the given Q+1 objects? So first of all, if E0 and everything else is arbitrary, we can always obtain a canonical system as the added new part in the reduced two-path graph system, right? If E0 is a canonical system and all the others are arbitrary, then we can still choose E1 tilde to be a canonical system because this inverse result always applies. It doesn't need that these Q were already canonical systems before. Now, if E0 was, for example, a Krein string, and the other strings were arbitrary, but in addition, we know that our function N0 that we constructed was a Stieltjes function, then we can also choose E1 tilde, the new part, to be a Krein string. If all the EJ were Stieltjes strings and N0 is a Stieltjes function, we can also choose E1 tilde to be a Stieltjes string. And now comes the disappointment. Well, if E0 or even all the EJ are Sturm-Liouville, we can only say that E1 tilde can be chosen to be a canonical system due to a lack of a general inverse result for Sturm-Liouville, unlike the others. So from this kind of overview, you can get already some feeling. When is this answer? Well, actually, I think the questions were posed in the different order at the beginning, So the structure of the reduced system, when can it be chosen of the same type? You will find the answers from here. What I haven't explained so far is in what sense do I mean, or do we prove that these two systems are equal? Well, this is specialized in one of our main results. This coinciding means that for the original system, which is a self-adjoint linear relation in such a product Hilbert space here, and for this reduced system, which is now only working in two Hilbert space components, because we replaced this second part by just one Hilbert space, the compressed resolvents compressed to the first red to the distinguished part coincide. So this means that if you take P0 and P0, the orthogonal projections of this big space and of the two component space, in both cases onto the first component, then the compressions of the resolvents to these first components coincide. Now, a little bit more maybe mechanically explained. So if on E0, you want to solve the Cauchy problem on the original star graph with a right-hand side, which has only one entry in the first component, and also a boundary, an initial condition with only an entry in the first component, then the solution coincides on E0 with the solution of the Cauchy problem of this reduced problem, where you just put a 0 in the smaller second component in H1 tilde. So somehow, if you imagine in the original picture, if this blue part is, for example, underground, and only the red part sticks out of the ground, and you look at you apply a force to this red part, then you can't tell. There could be a system with the original star graph underneath the ground, or there could be the reduced system underground. You couldn't distinguish just from how the solutions behave on the end that sticks out of the ground. Now, we go to a special case, also to make the loop to our first part of the talk, star graphs of Stieltjes strings. Now here, because we were so general and we can admit even Krein strings, we can also admit Stieltjes strings, but we can only admit Stieltjes strings where the masses accumulate at most at the outer vertices. So there may be infinitely many, but they should accumulate at most at the outer vertices. And we assume that in the middle, they are joined by a Robin type matching condition. So in this case, our results give the following. If all the edges are Stieltjes strings, and the phi j are the corresponding Weil-Titchmarsh functions corresponding to Neumann conditions at the center, V. Then, if the Robin parameter tau satisfies this inequality here, where these are the values, the limits from the left of the Weil-Titchmarsh coefficients of the individual Stieltjes strings, then there exists a single Stieltjes string E1 tilde joined to the distinguished edge E0 by standard matching conditions, such that the resolvent for the star graph G with Q+1 edges, and for the path graph G tilde with just two edges, namely E0 and E1 tilde, coincide on E0 in the sense that I explained on the previous slide. Now, this is just the recalling what a Stieltjes function was, because I want to explain to you what this condition star actually ensures. This condition star on the tau ensures that our n0, which in this particular case was given by that formula that we saw earlier, is indeed a Stieltjes function, because we know the phi j are Stieltjes functions, and if tau satisfies this condition, then so is n0. So now we know that every Stieltjes function admits a unique continued fraction expansion, even in the infinite case, by the Goldberg-Krein appendix. And so we can even find this Stieltjes string E1 tilde with its masses mk from this continued fraction expansion of our coefficient n0. Right? So we develop this n0 in a continued fraction expansion, and we can read off how this new system is constructed from there. So this is really a constructive procedure in the case of Stieltjes strings. Yeah, I think my time is really coming to an end. So here are the references about the part only about the Stieltjes strings, the two works with Slava Pivovarchik, and this last part that was published last year in complex analysis and operator theory. So what I would hope, actually, this is maybe the final comment. I mean, after all, locally a star graph, in a more complicated graph, the junctions are always star graphs, like junctions locally. So maybe this reduction result can help a little bit in considering also more complicated graphs and trying to reduce them by means of such procedures. I guess there are many people in the audience who know much more about these more involved graphs than I do. And so I think this is a good point to stop, and thank you very much for your attention.
Thank you very much, Christiane, for this.
May I ask a question?
Yes, I was going to offer to people to ask questions. Go ahead.
May I ask a question?
Yes, please.
So you referred many times to some book of Crane. What is it?
Oscillating matrices.
Yeah, but this is Gantmacher and Crane.
Sorry, Gantmacher-Krein. Sorry, I mixed it up. You know, Goldberg is a very common name in my other research. Sorry, it was correct on the slides, of course.
But this result is due to Gantmacher.
Well, it was correct on the slides. You know. So where are we? Where is this? Where is the here? Let's go back to the share. Can we go home? Wait a minute. Here.
Can I ask a question?
Yes, please. Sounds like, wait a minute. It sounds like Uzi.
My name is Uzi Smilansky.
I recognized your voice.
It's a comment. You see, everything that you did, and which I think understand, has a very analog in looking at the vertices as centers of scattering, because your construction and constructing, as you said in the last remarks that you had, that the complete graph is a mixture, is a union of many vertices. Each of them is a star. Is exactly the way that we are looking at quantum graph or discrete graphs, but from a scattering point of view, in which each vertex is a scattering center in a sense, and then you turn the equation of the secular equation for the complete graph into a different determinant problem. And I think, I'm pretty sure, I didn't work it out, of course, immediately, but also the fact that you have the Dirichlet to Neumann map is very much related to scattering. So I suggest, Christiane, that one of these days, when we are both confined to our respective homes, we can discuss it further, because it would be very interesting to look at the connection between the two different approaches. And thank you very much for a very interesting lecture.
Yeah, I would immediately believe that. I mean, what is maybe another point we were interested in then really to have also constructive procedures to solve inverse problems like we could for the Stieltjes string. But I think really this result has to be seen in the larger context of more complicated graphs. But yeah, at the moment I haven't been working on that anymore, but I'm really happy to discuss that. Thank you.
Okay. Thank you very much.
I wanted to ask, so there seems to be a relation between continued fractions and the distribution of zeros and poles, right?
Yes, yes.
So if you, maybe you can, if you let, at least in part one, if you just have a single string, if you let the length of a string increase, go to infinity, you could try to look at the limiting distribution of zeros and poles, right?
Well, I mean, the single string thing, I mean, this is really nothing that we did, right? This is old stuff from the,
So maybe someone else has done it.
Yeah.
But so it looks like if you sort of assume that some sort of limiting distribution, that you are generating lengths and masses randomly or in a certain way, then at least if you look at continued fraction expansions with more and somehow which do not terminate, which are infinite, then you look at least if you assume that some things are integers, for example, then you look at the orbit of some point in the complex plane under the action of some hyperbolic group, and you'll sort of be looking at maybe how it accumulates at infinity or on the real line or something like that. So and that is kind of a classical, also very old question. So I'm just wondering, probably if you maybe if you rig the problem that that M's and L's are of a certain special form, then you could use something about, you know, how points in an orbit of a Fuchsian group accumulate at infinity to say something about zeros and poles. But I'm not sure if it's interesting. Again, I'm not sure if anyone has done it, but perhaps this could be done. This
well,
just a thought.
To be honest, I can't seriously answer that, but I have another question, because you mentioned something actually to you. You said that the masses could be randomly distributed on the string.
Yeah, well, maybe
that will be very interesting for one of my co-authors, if I can make that remark. I haven't studied that, but yeah,
no,
so
thinking,
that was an interesting comment.
I'm just thinking that, you know, if you would need to do some renormalization because the masses have to add up to 1, but this, so if you just look at, you know, like continued fraction expansions, how fast the denominators increase and things like that. So this is related to like entropy of, I don't know. I like Svetlana Katok's book, you know, continued fraction, Fuchsian groups, or some classical books on continued fractions. So this is nice. Of course, I think in kind of in the classical situation, the masses and the lengths. So for let's say if you look at 2x2 integer matrices, then masses would have to be integer or something like that. But yeah, but there is some connection to this geometry of numbers on the hyperbolic plane.
Okay, thank you for the comment.
Thank you very much for the lecture.
Thank you.
Anyone else has questions or comments?
Alexander, if I could.
Yes, go ahead.
Michael. Yeah, Christiane, I'm wondering whether you have any bounds on the location of resonances.
No.
Because
well,
I think it links to the problem I showed you at some stage, sort of where we were doing with Brian, with a very specific never linear function.
Yeah. No, we haven't looked at that question.
Yeah.
Do you mean the problem you mentioned in February to me?
I think so. Yeah.
Yes.
I've been mentioning it to so many people so many times.
Okay.
So, yeah.
Okay. Yeah. It would be interesting to discuss.
Yeah, because there is the same representation in terms of never linear functions, continuous fractions, and you're basically looking at the location of zeros and poles but you want to restrict them to particular bounds uniformly, not asymptotically with them, but sort of uniformly with them.
No, resonances weren't on our radar at all yet.
You just mentioned them, so
yeah. So
I saw some similarity. Anyway, thanks.
Yeah.
But there are relations at the same top of sort of.
Yeah. Okay. Thank you. Nice.
Okay. Thanks.
Christiane, I have a simple question. Do you know if it's Alex? Do you know if there are results about optimization of eigenvalues with respect to where to place the masses?
Not that I know of. I mean, if you wanted to be sure, maybe I would ask either Slava Pivovarchik or Manfred Möller. You know, they wrote a book, or I'm not sure, is it already finished, but they are about to write, or it will appear in the OT series, but not that I know of.
Okay, thank you.
But to be on the safe side, I think Slava Pivovarchik follows everything. So even things that are not so closely related to what we were doing. So.
Thank you. Anyone else has a question or comments?
I was wondering one thing. I mean, it might be a clear consequence of the second part of the talk, but in the first part, when you were mentioning this inverse problem for the star graphs, you were assuming to know that Q, the number of Stieltjes string, was a given, right?
Yes.
And to me, it's, I mean, intuitively, and you know, my intuition could be very wrong, it seems like this would be the first thing that we should be able to recover from the spectrum, would be the number of Stieltjes strings. So are there actually isospectral, two systems with the same eigenvalues but different numbers of strings?
Well, one could imagine from the second part it might be possible, but on the other hand, this coincidence is only on this distinguished edge. So that is a bit, of course, this distinguished edge will not contain all the information on the spectrum. So difficult to say, but we didn't study the question of considering also to reconstruct the Q. Yeah, right. But definitely that is a more difficult problem.
Thank you very much, Christiane. I think we will stop here for today.
Thank you for listening.
Thank you for the very nice talk.